Welcome back to the Deep Dive. We're the place where we tackle some of the universe's biggest, most, well, astounding concepts.
And try to give you the most important insights.
Exactly. All wrapped up with maybe a bit of wonder and, honestly, sometimes a dash of existential awe.
It comes with the territory.
It really does. And today, we're facing something truly magnificent, but also, let's be honest, utterly terrifying.
Objects that really push our understanding of, well, everything. Space, time, reality itself.
We are talking about the cosmos's ultimate voids, those infamous points of no return, black holes. Okay, let's unpack this. Today, we're plunging deep, really deep into the most extreme objects the cosmos has to offer.
And they really are extreme.
Black holes aren't just, super dense objects. They are effectively literal rips in the fabric of existence.
Pushing the known laws of physics right to their absolute breaking point.
And in doing so, they reveal something really profound, something fundamental about how our universe is put together. They're cosmic enigmas, really.
They absolutely are. And they invite us to rethink almost everything we thought we knew. And that's basically our mission with this deep dive today, isn't it?
Yeah.
We want to scientifically deconstruct these fascinating objects, get past the usual sci-fi stuff, which is fun, but
And not the whole picture.
exactly. We want to understand the incredible physics that makes them tick. And our guide for this journey is a really fantastic source, The Ultimate Abyss, a journey into black holes. It's a masterful exploration.
It really lays things out clearly.
It does. So we're going to pull out the most important nuggets of knowledge from that text. The goal is you leave feeling not just, informed.
But maybe with a few of those aha moments.
Hopefully.
Yeah.
Some genuinely mind-bending insights. We'll take a journey starting with rethinking gravity itself.
Which is fundamental.
Absolutely. Then through their violent births. And, well, all the way to a theoretical look at what happens if you take the plunge.
Terrifying look.
It is a bit, yeah.
So get ready. This is going to be a genuinely fascinating experience. We're aiming to give you a direct path to understanding a topic that often feels just impossibly complex.
But hopefully without the overwhelm.
Right. We're going to explore concepts that will, I think, definitely change how you look at gravity, time, and maybe the very fabric of the universe. Let's dive in. Okay. Now, before we can even begin to really get our heads around the incredible nature of a black hole, we need to do something fundamental.
Which is?
We need to shift our perspective completely on something we experience literally every second of every day: gravity.
Right. That everyday force.
Yeah. Most of us, we grow up with this sort of intuitive, almost simplistic idea from Newton: gravity as a simple, invisible pulling force.
The apple falling from the tree?
Exactly. The Earth pulls the apple down, and look, it works fine for launching rockets or building bridges, right? It's effective for everyday life.
It gets the job done for most things, sure.
But it's really just the tip of the iceberg, and that Newtonian picture, it won't get us anywhere near understanding black holes.
You're absolutely right. That intuitive view, Newton's view, while obviously groundbreaking for its time,
Oh, completely. Changed the world.
it treats gravity as a force acting within a static stage of space and time. But then came Einstein.
1915, general relativity.
Exactly, and he completely revolutionized that understanding. It wasn't just an improvement on Newton, it was a radical reimagining.
Far more elegant, too, isn't it?
Incredibly elegant, yes.
Yes.
And ultimately more accurate. He saw gravity not as a force at all, but as a consequence of the universe's geometry, the shape of things. Einstein proposed that space and time, they aren't separate. They're not just static concepts that things move through.
Which is how we tend to think of them.
It is, but he said they are inextricably woven together, linked into a single dynamic four-dimensional fabric. He called it space-time.
The famous space-time fabric.
And here's the key part. Matter and energy warp this fabric. They distort it. To really get a feel for this, let's go back to that classic analogy which our source, The Ultimate Abyss, explains really well.
The trampoline one.
That's the one. Imagine a huge, flat, taut trampoline stretched out in front of you. Now, this isn't just a metaphor for space. It represents the whole fabric of space-time.
Okay, got the image.
Now, you place a heavy bowling ball right in the center. What happens?
It sinks down, makes a dip. The fabric sags.
Exactly. It sags, it curves under the bowling ball's weight. And that curvature, that dent, that deformation in the fabric, that is Einstein's gravity.
So it's not the ball pulling things.
No, it's not some invisible pull coming from the ball. It's a direct consequence of the ball's mass distorting the very stage, the space-time, that everything else exists on. Now think about rolling a small marble across that trampoline, a little ways away from the bowling ball.
Okay.
That marble isn't being directly pulled by the bowling ball in Einstein's view. Instead, it's just trying to follow the straightest possible path it can across that curved surface.
Yeah, but the surface isn't flat anymore.
Precisely. So from the marble's own perspective, it thinks it's going straight. But if you're looking down from above...
It looks like it's circling the bowling ball, like it's in orbit.
Exactly. It appears to be orbiting because the curvature of the fabric dictates its path. And that's a near-perfect analogy for our solar system,
The sun is the bowling ball.
creating this huge gravity well, this big curve in space-time around it.
And the Earth is the marble.
Yep. Just constantly trying to move forward in a straight line through that curved space-time. And that curved path is what we see as its stable elliptical orbit.
Wow. It's really beautiful when you think about it that way. Gravity as geometry.
It is. It's incredibly elegant. The geometry of the universe itself tells things how to move.
So it's not a pull, it's a curve.
Right.
That's a huge mental shift. It makes gravity feel much more fundamental, a part of the universe's structure itself.
It does, rather than some external force acting upon it. And this dynamic interplay, this relationship, is just perfectly summed up by the physicist John Archibald Wheeler.
Oh, the famous quote.
The famous quote, yeah. Space-time tells matter how to move, matter tells space-time how to curve.
It's so concise, it's reciprocal.
It is. That quote is really central to understanding general relativity. Matter, anything with mass or energy warps space-time, makes these gravity wells.
And then the warped space-time tells other things, even light, how to move through it.
It's a cosmic dance, essentially. The stage itself is shaped by the dancers, and then the shape of the stage guides their steps. It's revolutionary. It unites space, time, and gravity into one geometric picture. Okay, now, here's where it gets really interesting. Connecting this directly back to black holes.
Right, the ultimate curve.
Exactly. Let's push that trampoline analogy even further. Imagine that bowling ball, representing some star or object, became so impossibly heavy, so incredibly dense.
More than just a dent.
Way more. Imagine it doesn't just dent the trampoline or create a deep well. Imagine it rips a hole straight through it.
Yeah.
It creates a bottomless, vertical funnel. An infinite well that nothing, absolutely nothing, can climb out of.
So that's what a black hole is in this picture.
In this context, yes.
Yeah.
It's a region where an immense amount of mass has been crushed into such an unbelievably tiny volume.
The singularity we hear about.
We'll get to that. But the result is that the curvature of space-time becomes, well, effectively infinite. It's not just a curve anymore, it's a tear, a literal abyss in the fabric of the universe.
Fundamentally changing the geometry around it.
Permanently.
Wow. Okay, so that shift in understanding gravity from force to distortion, it's not just important, it's absolutely foundational, isn't it?
It's everything.
It's the only way we can even begin to comprehend the true, utterly bizarre nature of black holes. They're not just dense objects. They're actual distortions, tears in reality itself.
Born from gravity's ultimate triumph over all other forces.
And what's really wild, thinking about the history of this idea, the basic concept of dark stars, objects so dense that light can't escape, that actually predates Einstein by quite a bit.
It does, remarkably so, over a century earlier.
It shows that people were pondering these extreme possibilities long before we had the theoretical tools to really describe them.
It's an incredible intellectual lineage, yeah.
Yeah.
The very first person to really reason this out, using the physics available at the time, was an English natural philosopher named John Michell.
Back in the 1700s.
Back in 1783, believe it or not. Using purely Newtonian physics, Michell conducted this brilliant thought experiment.
What did he figure out?
He theorized that if you had a star that was sufficiently massive but also incredibly compact, its gravitational pull would be so immense
That nothing could leave.
that the escape velocity, the speed you need to break free from its gravity, would actually be greater than the speed of light.
Wow, even using Newton's ideas.
Exactly.
Mm-hmm.
And since light has a finite speed, he reasoned, it would be trapped. The star would be invisible. He called it a dark star.
A dark star. That's remarkably close.
It's an astonishing insight for his time, absolutely. But it was still based on that Newtonian pulling idea, thinking of light as particles being pulled back. It didn't have the framework of warped space-time.
It lacked the general relativity piece.
Right. The modern understanding really kicks off in 1915, literally just weeks after Einstein published his field equations for general relativity.
That quickly.
Amazingly quickly. A German physicist named Karl Schwarzschild, who was actually serving on the Russian front during World War I, Quite a setting.
No kidding.
He found the very first exact solution to Einstein's incredibly complex equations. His solution described the gravitational field just outside a single, non-rotating spherical mass, like a simple star.
And what did he find in that solution?
He found something peculiar, a mathematical feature, a specific distance from the center of that mass, a radius.
The Schwarzschild radius.
That's the one, named after him. It was a boundary, defined by the math, where space-time became so warped that nothing, not even light, could escape from within it.
So the math itself predicted black holes right out of the gate.
Directly from Einstein's theory, yes, the first theoretical prediction.
So you'd think everyone would immediately say, wow, these things must exist. But that wasn't the case, was it? Even Einstein had doubts.
It seems almost contradictory, doesn't it? His own theory predicts them, yet he was skeptical.
Why the hesitation?
Well, it speaks to the scientific caution of the time, I think. For decades, this Schwarzschild radius was largely treated as just a mathematical oddity. A quirk in the equations, maybe, or something that wouldn't happen in the real universe.
An artifact of the math.
Possibly. Even Einstein himself was quite doubtful that real stars could actually collapse down that far. He thought some other force, maybe something we didn't know about yet, would inevitably halt the collapse before it reached that point. The idea was just too extreme, too weird.
So when did that change? When did scientists start taking them seriously?
That really shifted in the 1960s. Two things came together. First, we gained a much better understanding of stellar evolution, how stars live and die.
Right, the life cycles of stars.
And second, there was the absolutely profound theoretical work done by physicists like Roger Penrose and Stephen Hawking. They used general relativity with incredible rigor.
What did they show?
They demonstrated mathematically that gravitational collapse wasn't just possible for sufficiently massive stars, it was inevitable. Once a massive star runs out of fuel, if its core is above a certain mass limit, nothing in known physics can stop it from collapsing all the way down to a singularity.
No escape. Gravity wins.
Gravity wins. Their work basically forced the scientific community to accept that, according to Einstein's own theory, black holes must be real. They weren't just mathematical curiosities anymore. And then finally, the observational evidence started to catch up with the theory. Slowly at first, but then more and more convincingly.
Turning math into reality.
Exactly. A big moment was in the 1970s with Cygnus X1.
What was that?
Cygnus X1 is an X-ray binary system. Astronomers saw a massive visible blue supergiant star orbiting something invisible.
Orbiting empty space?
Well, orbiting something incredibly compact and massive that wasn't emitting visible light, but the system was blasting out X-rays.
How did they know it was a black hole?
By studying the blue star's orbit very carefully, they could calculate the mass of its unseen companion. And it turned out to be way too massive to be a neutron star, the other possible compact remnant of a star's death.
It crossed that mass limit you mentioned.
Precisely.
Yeah.
And the intense X-rays were perfectly consistent with gas being torn off the blue star, heating up to millions of degrees in an accretion disk as it spiraled into a black hole. Cygnus X1 became the first really strong black hole candidate.
A major turning point.
Definitely shifted things from theory towards observation. And then, much more recently, we've had these just stunning, almost direct detections.
You mean gravitational waves?
Exactly. Observatories like LIGO in the US and Virgo in Italy. These incredible instruments detected gravitational waves, literal ripples in the fabric of space-time itself.
Shakes in the cosmic trampoline?
A perfect way to put it? These ripples are generated by the most violent events, particularly the mergers of distant black holes.
When two black holes collide.
Yes. They spiral into each other and merge in this cataclysmic event. LIGO and Virgo work like giant microphones, listening for these tiny space-time vibrations.
Using lasers.
Yeah, incredibly precise laser interferometers. The first detection, GW150914, back in 2015, was the unmistakable chirp sound.
The sound of space-time ringing.
Of two black holes, about 30 times the mass of the sun each, merging over 1 billion light years away. It was direct proof of merging black holes and a stunning confirmation of general relativity.
That's mind-blowing, hearing black holes collide.
It opened a whole new way to study the universe.
Yeah.
And then, maybe even more astonishingly, we got the pictures.
The Event Horizon Telescope.
The EHT, yeah, an incredible achievement. They linked up radio telescopes all across the globe.
Creating a virtual telescope the size of Earth.
Effectively, yes. Giving them the resolution to zoom in on the immediate vicinity of supermassive black holes, like the one at the center of the M87 galaxy.
And what did they see?
They imaged the black hole's shadow. They saw this bright ring of superheated gas swirling around the event horizon with a dark patch in the middle. the region where light can't escape.
Direct visual evidence. The silhouette of the abyss.
Exactly. A bright donut surrounding the darkness. It was a monumental moment, providing direct visual proof of their existence and the extreme warping of space-time right near the edge.
That whole journey, it's just incredible. From a philosophical idea about dark stars centuries ago
Through Einstein's math, decades of doubt.
to finally getting undeniable proof from colliding black holes and actual images. It's such a testament to theoretical prediction meeting human ingenuity.
And technological advancement pushing the frontiers.
Yeah.
It shows how far we can really push our understanding.
So, okay, we know they exist. We've seen their effects, even their shadows. But how do these cosmic monsters actually come into being? What does this all mean for stars and galaxies?
It means getting into the birth process.
Understanding how these behemoths are born. And it sounds like one of the most dramatic stories in the cosmos, right? A kind of ultimate battle.
It truly is. At its very core, black hole formation is all about a fundamental battle happening inside stars.
A cosmic struggle.
Throughout a star's life, there's this constant fight going on. You have the immense outward pressure from nuclear fusion in its core.
The star trying to blow itself apart.
Essentially, yes.
Yeah.
That fusion is burning lighter elements to heavier ones, releasing huge amounts of energy. And that outward push is constantly fighting against the relentless inward crush of the star's own gravity.
Gravity trying to pull it all together.
As long as fusion is happening, there's usually a balance, a stable equilibrium. The star holds its shape.
But for a black hole to form,
Gravity has to win. And it has to win decisively, catastrophically. Let's start with the type we perhaps talk about most often, stellar mass black holes.
the smaller ones,
Yeah.
relatively speaking.
Relatively speaking, yes, though still incredibly massive compared to planets. These come from the spectacular death of truly massive stars. We're talking stars born with more than about, say, 20 to 25 times the mass of our own sun.
The real giants. O-type stars.
Exactly. These giants burn through their nuclear fuel incredibly fast. They live fast and die young, cosmically speaking.
What happens when the fuel runs out?
When a star like that finally exhausts its usable nuclear fuel, meaning its fused elements all the way up to iron in its core.
Iron is the endpoint for fusion, right? Doesn't release energy.
Correct. Fusing iron actually consumes energy. So that outward pressure from fusion suddenly stops, like turning off a furnace. There's nothing left to hold the star up against its own immense weight.
So gravity takes over.
Instantly and catastrophically. The core collapses inwards under its own gravity in just fractions of a second. This incredible implosion triggers a massive rebound shockwave.
A supernova explosion.
Exactly. A Type II supernova. A titanic explosion that blasts the star's outer layers out into space, creating beautiful nebulae, but also seeding the universe with heavy elements. It can briefly outshine its entire host galaxy.
An unbelievably violent event.
Absolutely. But here's the crucial part for black hole formation. What happens to the core after the explosion?
The bit left behind.
If that remnant core, after the supernova has blasted away the outer layers, is still more massive than about 3 times the mass of our sun.
That's the limit you mentioned earlier, the Tolman-Oppenheimer-Volkoff limit.
That's the one. It's basically the maximum mass that a neutron star, the other possible dense remnant of a supernova, can possibly sustain before collapsing further.
So if the core is heavier than that,
Then no known force in the universe can stop its continued collapse. Not even the incredible pressure of neutrons packed shoulder to shoulder called neutron degeneracy pressure. Gravity just overwhelms everything.
and nothing can hold it up.
Nothing. It crushes the core down, down, down into an unbelievably small point of theoretically infinite density. The singularity.
And that's it. A black hole is born.
A stellar mass black hole is born. A remnant of a star's violent death. A monument to gravity's ultimate power.
Okay, so that's one way, the dramatic death of a single really big star. But then you hear about these absolutely enormous ones, the supermassive black holes.
The monsters in the middle of galaxies.
Yeah, they seem to rule entire galaxies. How do those form? Because that can't just be one star collapsing, can it? The scale is just wrong.
You're absolutely right. The scale is completely different. Millions to billions of times the sun's mass. And their formation story is definitely more complex and, honestly, still an active area of research with some unanswered questions.
Not as clear-cut as the stellar one.
Not quite. Supermassive black holes, or SMBHs, are the behemoths we find lurking at the centers of almost all large galaxies, including our own Milky Way. We have Sagittarius A, pronounced A star, at our center.
SGRA. About 4 million times the mass of the sun, right?
Roughly, yes.
Yeah.
And that's actually modest compared to some, which reach billions of solar masses. How they got so big is the big question.
So what are the main ideas?
Well, there are a few leading theories, and likely a combination of them is responsible. One possibility involves the very early universe, maybe just a few 100 million years after the Big Bang.
What happened then?
Huge clouds of primordial gas, mostly hydrogen and helium, might have collapsed directly into black holes without forming stars first. These direct collapse black holes could have formed seeds that were already tens or hundreds of thousands of times the mass of the sun.
So they started out much bigger than stellar black holes.
Potentially, yes. Another major factor is mergers. Galaxies collide and merge all the time throughout cosmic history.
And when galaxies merge.
Their central supermassive black holes eventually find each other, spiral inwards due to gravitational wave emission, and merge too, creating an even larger black hole.
So they grow by eating each other.
Effectively, yes.
Oh.
And they also grow by constantly feeding on the material around them in the galactic center. Gas, dust, unfortunate stars that stray too close. Exactly. They accrete vast amounts of matter over billions of years. This steady feeding, which can make the galactic center incredibly bright, what we call an active galactic nucleus, or AGN.
Like quasars.
Quasars are a type of AGN, yes. This accretion process allows them to accumulate that immense mass we see today. It's a much more gradual, but ultimately galaxy-shaping process, very different from the explosive birth of a stellar mass one.
It's just mind-boggling, the sheer range, from a single star's death cry to this slow, dominant growth that shapes entire galaxies over cosmic time.
It really highlights the diverse and extreme ways gravity operates in the universe, dictating fates on all scales.
Okay, let's unpack this a bit more. If we could somehow, theoretically take a peek inside a black hole, what would we actually find? It's not just empty darkness, is it?
No, not at all. It's structured in a very bizarre way.
We talk about these key components, these parts that define what a black hole is, and each one seems stranger than the last.
That's a good way to put it. Okay, let's dissect the anatomy. Right at the very heart, the absolute core is the singularity.
The point of infinite density.
Theoretically, yes. It's imagined as a one-dimensional point-zero volume where all the mass of the original collapsed object has been crushed.
All that star stuff in literally no space.
That's the theoretical description. And it's a place where our current understanding of physics just stops working. General relativity predicts infinite density and curvature, but quantum mechanics likely has something to say about that at such small scales.
So it's where GR and quantum mechanics clash.
It's the ultimate clash point. We need a theory of quantum gravity, which we don't have yet, to truly describe what happens at this singularity. It's a major frontier in physics.
Okay, so the singularity is the center. Then there's the most famous part.
The event horizon, the point of no return.
The edge.
Exactly. But it's crucial, really crucial to understand what it is and isn't. It is not a physical surface.
You wouldn't bump into it.
No wall, no membrane you could touch. It's purely a boundary in space-time, an invisible sphere surrounding the singularity.
What defines that boundary?
It's defined by the radius at which the escape velocity, the speed you'd need to get away from the black hole's gravity, becomes equal to the speed of light.
And since nothing can go faster than light,
nothing that crosses that boundary can ever get back out. Matter, energy, light itself. It's all trapped. All possible paths beyond the event horizon lead inevitably towards the singularity. It's a one-way door in space-time.
Chilling. So, if the black hole itself, inside the event horizon, is invisible because light can't escape, how do we even know they're there? How do we see them?
That's an excellent question. We don't see the black hole directly, but we often see the chaos it creates around itself. This usually comes in the form of an accretion disk.
The swirling disk of doomed matter.
Pretty much, yeah. When gas, dust, or even shredded stars get pulled towards a black hole, they rarely fall straight in because they have some sideways motion, some angular momentum.
They start orbiting.
They form a vast spinning disk around the black hole. Think of water swirling down a drain, but on cosmic scale and much, much hotter.
Wow.
Extreme friction between the particles in the disk as they rub against each other at incredible speeds, plus intense tidal forces and magnetic fields. All this heats the matter up to millions, sometimes even billions of degrees.
Hot enough to glow.
Incredibly brightly. This superheated plasma glows fiercely across the electromagnetic spectrum, especially in X-rays, but also visible light, radio waves. This glowing disk is the clear signpost.
It's the light around the black hole that gives it away.
Exactly. These accretion disks can be astonishingly bright, sometimes outshining all the stars in their host galaxy combined. That's how we detect many black holes, especially the supermassive ones. Now, we also classify black holes based on their properties, which adds another layer of interest. The simplest theoretical type is the Schwarzschild black hole,
Named after Carl Schwarzschild.
the very same. This is the idealized case. It only has mass, and it's not spinning. It's perfectly spherical and static. It's the one his original solution described.
But is that realistic? Do stars not spin?
Most things in the universe spin. Stars spin, galaxies spin. So it's much more likely that real black holes also spin. And for those, we have the Kerr black hole model.
Named after Roy Kerr, who found that solution.
Correct. A Kerr black hole has both mass and angular momentum it spins. And this spin introduces some really weird and wonderful physics.
Like frame dragging.
Exactly. Frame dragging is one of the most fascinating predictions. The spinning black hole literally drags space-time around with it, like a rotating ball submerged in thick syrup would drag the syrup around.
Space-time itself gets twisted.
It gets dragged along in the direction of the black hole's rotation. This affects the orbits of anything nearby. It also creates another region outside the event horizon called the ergosphere.
Ergosphere.
Yeah. Within the ergosphere, space-time is being dragged so intensely that it's literally impossible for anything to stay still relative to a distant observer. You have to move in the direction of the black hole's spin, even if you fired your rockets full blast the other way.
Whoa! You're forced to rotate with it.
We're dragged along by the swirling space-time. It's a direct consequence of general relativity, this lens-thirring effect, and it has subtle but measurable effects.
Wow. So these components, the singularity at the core, the event horizon as the point of no return, the blazing accretion disk showing us where they are, and then the weirdness of spin and frame dragging.
They all combine to paint a picture of these incredible objects.
And they let us study them, classify them, even see their influence from light years away, even though the heart remains hidden in ultimate darkness.
It's truly awe-inspiring how much we can deduce from the way they distort their surroundings.
Okay, here's where it gets really interesting. And maybe more than a little terrifying.
A plunge.
The plunge. What if you, our listener, were on that unlucky, unavoidable path straight towards a black hole? What would that actually be like? Let's take that speculative, maybe harrowing journey into extreme physics.
It's definitely a journey into the utterly alien, where our everyday understanding of reality just gets twisted beyond recognition. Okay, let's imagine you're an astronaut, falling towards, say, a stellar mass black hole.
Feet first, I suppose. Does it matter?
It will matter later, tragically. But let's start from the perspective of someone watching you from a safe distance, far outside the event horizon.
What would my friend see?
Long before you reach the edge, things would start looking very strange for you from their viewpoint. The first big effect is gravitational time dilation.
Time slows down near heavy things.
Exactly. As you get closer to the black hole where gravity is stronger, your clock would appear to tick slower and slower compared to your friend's clock far away.
So I'd look like I'm moving in slow motion.
Increasingly slow motion, yes. Your actions would seem to stretch out over longer and longer periods from their perspective. You're experiencing time differently. At the same time, there's gravitational redshift.
The light stretching out?
Right. The light coming from your spacesuit, struggling to climb out of that deepening gravity well, loses energy. Its wavelengths get stretched longer.
So I'd look redder.
Redder and dimmer. The light shifts towards the red end of the spectrum, and less of it reaches your friend. Now, combine these two effects, time slowing down, light getting redder and dimmer. What does your friend actually see?
A slow, red, fading version of me.
Exactly. They'd see your descent slow to a crawl, you'd get redder, dimmer. And then as you approach the event horizon, you would appear to freeze. Just hover there, motionlessly, at the very edge.
Frozen in time.
From their perspective, yes. You'd seem to take an infinite amount of time to actually cross the horizon. Eventually, the redshift would become so extreme that you'd fade from view entirely. To them, you never truly fall in. You just become this infinitely stretched, infinitely dim ghost plastered on the edge.
That is deeply weird and kind of disturbing. A permanent frozen image at the abyss.
It's one of the paradoxes of perspective near a black hole.
But, okay, that's what they see. What about me? The one actually doing the falling. Do I feel time slow down? Do I notice crossing that event horizon? Is there like a jolt or a sign?
This is where it gets even stranger, perhaps. From your perspective, falling in, time would feel completely normal. Your watch would tick at its usual rate. You wouldn't feel like you're in slow motion at all.
Business as usual, time-wise?
For you, yes.
Yeah.
And crucially, as you cross the event horizon, you would feel absolutely nothing.
So bump. No barrier.
No physical sensation whatsoever. Remember, it's not a surface, it's just a boundary in space-time. You'd sail right across it without even knowing, most likely.
But the moment I cross.
Your fate is sealed. Irrevocably. The instant you pass that threshold, all possible future paths, every direction you could possibly try to move, inevitably leads inward towards the singularity.
The geometry traps you.
The geometry of space-time inside the horizon is warped, such that the future direction for everything points only towards the center. There's no path leading back out. It's a one-way trip, and you probably wouldn't realize you'd passed the point of no return until, until things got unpleasant. And that brings us to the truly grim part, the inevitable end once you're inside.
Spaghettification. It even sounds horrible.
It is, and it's caused by extreme tidal forces. These aren't the gentle tides we see on Earth. These are tidal forces gone absolutely wild.
How does it work?
Okay, let's go back to you falling feet first. As you get closer to the singularity, the gravitational pull is increasing incredibly rapidly.
Stronger on my feet than my head.
Exponentially stronger. The difference in the gravitational force pulling on your feet compared to the force pulling on your head becomes immense. This differential force is the tidal force.
And that stretches me.
It stretches you vertically, pulling your feet away from your head with unbelievable force. At the same time, because all the force is directed towards the single point of the singularity, you also get squeezed horizontally from the sides.
Stretched and squeezed.
Into a long, thin stream of atoms. Like, well, a piece of spaghetti. You'd literally be torn apart, molecule by molecule, atom by atom.
Ugh, that's vivid.
It's the grim reality of extreme gravity gradients. Now, there's an interesting twist here, depending on the size of the black hole.
It happens differently for small ones versus big ones.
Yes. For a stellar mass black hole, maybe a few times the mass of the Sun, it's relatively small and incredibly dense. The event horizon is quite close to the singularity.
So the gravity changes really fast near the edge.
Exactly. The tidal forces become overwhelmingly strong very quickly as you approach. So for a stellar mass black hole, spaghettification would actually happen before you even reach the event horizon.
You'd be ripped apart while technically still outside the point of no return.
Bizarrely, yes. You'd be turned into spaghetti in a region where escape is theoretically possible, if you could survive being spaghetti and travel faster than light. Which, obviously, you can't.
Okay, what about the big ones? Supermassive black holes.
For a supermassive black hole, millions or billions of times the Sun's mass, its event horizon is much, much larger. It's much farther away from the central singularity.
So the gravity gradient is gentler at the edge.
Much gentler. The tidal forces at the event horizon itself are actually quite weak, surprisingly. So you could, in theory, cross the event horizon of a supermassive black hole completely intact.
You'd feel nothing, just sail right in.
You'd feel nothing special as you crossed. You'd be doomed, of course, but comfortable for a while. The spaghettification would only happen much later, much deeper inside, as you got significantly closer to the singularity on your final inescapable journey.
So a gentler initial crossing with the same grim end.
The same grim end. Either way, your constituent atoms eventually reach the singularity, which is, as we said, effectively the end of space and time as we understand them, where our physics gives up.
Puts a whole new horrifying spin on getting stretched thin, doesn't it?
It certainly does.
I think I'll avoid demonstrating that one. But that chilling reality spaghettification, it just perfectly illustrates how utterly extreme an alien gravity becomes near a black hole.
It really pushes our intuition to the breaking point.
It reminds us just how profoundly weird the universe can be in its most extreme corners. But what's really fascinating here is, this isn't a closed book, is it? Our understanding of black holes is far from complete. It feels like it's still evolving really rapidly.
Absolutely.
They aren't just things we figured out in the past. They're active frontiers. They're still surprising us.
Constantly. Black holes remain one of the most exciting, most dynamic frontiers in modern physics. They're driving discovery and seriously challenging our most fundamental ideas about the universe.
And we have these incredible new ways to study them now, ways Einstein couldn't have imagined.
Exactly. Take gravitational waves again. LIGO and Virgo haven't just detected black hole mergers once. They've detected dozens now.
Building up a catalog?
Building a catalog, yes. Allowing us to study the populations of black holes, their masses, their spins, how often they merge. It's giving us unprecedented data on the dark side of the universe. We're literally listening to the universe shake as these things collide.
Hearing the space-time symphony.
That's a whole new sense for astronomy. And it's testing general relativity in these incredibly strong gravity regimes with mind-boggling precision. So far, Einstein's theory is holding up beautifully. And then there's the deep theoretical work, like Stephen Hawking's legacy.
Hawking radiation, the idea that black holes aren't entirely black?
Precisely. His groundbreaking work in the 1970s brought quantum mechanics into the picture. He showed that due to quantum effects right near the edge of the event horizon.
Weird quantum fuzziness.
Sort of, yeah. Virtual particle-antiparticle pairs are constantly popping into and out of existence everywhere in space, even in a vacuum. Hawking realized that if a pair pops into existence right at the event horizon, one particle might fall in while the other escapes.
And the escaping one carries energy away.
Exactly. To a distant observer, it looks like the black hole is emitting particles, like it has a faint temperature. This is Hawking radiation.
And it means black holes evaporate.
Very, very slowly, yes. The escaping particle effectively carries away a tiny bit of the black hole's mass energy over truly immense timescales far longer than the current age of the universe. For typical black holes, they should theoretically evaporate completely.
Wow. So they have a lifespan, albeit an incredibly long one.
It was a revolutionary idea, bridging general relativity and quantum mechanics in a completely unexpected way.
But that bridge, Hawking radiation, it also leads directly to one of the biggest headaches in modern physics, doesn't it?
Oh yes, the big one.
The information paradox. It sounds like it puts our two best theories of the universe head to head.
It does exactly that. It's arguably the most famous, most profound puzzle related to black holes, and it cuts right to the core of what we think reality is made of.
So what's the conflict? GR versus QM.
Precisely. On one side, you have Einstein's general relativity. According to GR, when something falls into a black hole, the detailed information about what it was, whether it was a book, a star, an astronaut, seems to be lost forever behind the event horizon. And when the black hole eventually evaporates via Hawking radiation, that radiation seems to be purely thermal random. It doesn't carry the specific information about what fell in.
So GR says information is destroyed. Gone.
Effectively, yes. It gets crushed out of existence at the singularity, and the evaporation doesn't bring it back.
But quantum mechanics says.
Quantum mechanics, our fantastically successful theory of the small, has a fundamental principle. Information is always conserved. It can never be truly destroyed.
It can be scrambled, hidden, rearranged.
But the underlying quantum information describing the state of a system must, in principle, always be recoverable. If you burn a log, the information isn't lost. It's encoded, albeit complexly, in the smoke, the ash, the heat, the light. Quantum mechanics insists information loss is impossible.
So the paradox is, where does the information go when a black hole evaporates?
Exactly. Does it disappear forever, violating quantum mechanics, or does it somehow get out, potentially violating general relativity's description of the event horizon as a perfect one-way membrane?
It's a direct contradiction between our two best theories.
A major clash. Resolving it is one of the biggest driving forces in theoretical physics today, pushing towards a theory of quantum gravity. How do you reconcile these two pillars of modern science?
What are some of the ideas? How might information get out?
Oh, there are many wild ideas. Some physicists propose things like the holographic principle. Maybe the information isn't inside the black hole at all, but somehow encoded on the 2D surface of the event horizon, like a hologram storing 3D information.
So the information never truly falls in.
Or perhaps it does, but it gets imprinted on the outgoing Hawking radiation in some incredibly subtle way that we don't yet understand. Stephen Hawking himself later proposed that maybe information isn't lost, but stored in a sort of fuzzy way at the horizon and released scrambled.
Then there are more radical ideas, like firewalls.
Yes, the firewall idea suggests that maybe crossing the event horizon isn't smooth after all. Maybe there's an incredibly energetic barrier there that destroys anything falling in, releasing the information immediately. But that creates its own problems with general relativity's principle of equivalence.
It sounds like we're far from a solution.
We are. It's a deep, deep problem, and the solution likely requires a fundamental shift in how we think about space-time, gravity, and quantum information itself. It's a clue, perhaps the biggest clue we have, pointing towards the next revolution in physics.
It's just incredible, isn't it? Even with everything we've learned, the direct detections, the images, black holes still pose these absolutely fundamental questions.
They keep challenging us.
They challenge our most successful theories and basically demand that we dig deeper, think harder. They really are these ultimate cosmic laboratories.
Testing physics at its absolute limits.
So what does this all mean? Thinking back on our journey today, it's been quite something.
It really has.
We started by completely reimagining gravity, right? Moving from that simple Newtonian pull to Einstein's elegant space-time trampoline, seeing gravity as curvature.
A fundamental shift in perspective.
Then we traced the whole history, Mitchell's dark star idea, Schwarzschild finding them in Einstein's math, the decades of skepticism.
Until Penrose and Hawking showed they were inevitable.
And then, boom. Observational proof from Cygnus X1, LIGO's gravitational waves, the EHT's incredible images.
From theory to reality.
We looked at how they're born, the explosive death of giant stars for the stellar ones, the slow merging and feeding for the supermassive giants shaping galaxies.
Two very different paths to creating these monsters.
And then we took that terrifying theoretical plunge inside.
Yeah.
Thinking about time dilation, redshift from afar.
And the horrifying reality of spaghettification up close.
It really drives home that black holes are the universe's ultimate expression of gravity's power.
Born from stellar death, defining the centers of galaxies, and representing the absolute limits of our current physics. And crucially, they're no longer just theoretical ideas on a blackboard. They are real, observable objects out there in the cosmos.
We can see their shadows, hear their collisions.
Exactly. They serve as these incredible natural laboratories for testing physics under conditions we could never replicate here on Earth. Conditions of extreme gravity, extreme density.
Pushing GR and QM to their breaking points.
And as our telescopes and detectors get even more powerful, these elegant, terrifying abysses will undoubtedly keep challenging our theories. They'll keep forcing us to refine our understanding of that cosmic battle between matter, gravity, space, and time.
They hold keys to deeper understanding.
They absolutely do, which leads to a final kind of provocative thought to leave our listeners with.
Okay, let's hear it.
Thinking about that information paradox again. If it turns out that information truly is lost when a black hole evaporates, violating that core principle of quantum mechanics, what would that imply about the fundamental nature of reality itself?
That the universe isn't as orderly as quantum mechanics suggests.
Perhaps. Or maybe resolving the paradox. Finding out how information is preserved will force us to completely reshape our understanding of space-time. Maybe revealing it to be emergent, holographic, or something even stranger. How might figuring this out rewrite the most basic rules of the universe?
Yeah, that's powerful stuff to chew on. What does information loss or its preservation really tell us about everything?
It's a question driving physics forward, and the answer, whatever it is, will likely be profound.
Indeed. Well, thank you for joining us on this incredibly deep dive into the ultimate abyss. It's been mind-bending.
Always a pleasure to explore the extremes.
Keep looking up, keep asking those big questions, and keep exploring these cosmic wonders with us. Until next time on the Deep Dive.